Hello, this is Mr. Labradorf, and we're taking notes today on section 2.6, higher order derivatives. Essentially what a higher order derivative is when we have to take derivatives upon derivatives upon derivatives. Okay, so we're looking for the rate of change of different rates of change. Now, we've already talked about the first derivative and the first derivative notation, which is either y prime, f prime, and dy dx. The other notations that you see here are typically used to denote when we are taking derivatives of functions. But we can expand upon these by also talking about second, third, fourth, and nth derivatives. And you notice there's some commonalities here. First, in our second derivative, we have y double prime or f double prime of x. Lesser notated notation would be d 2y of dx2, or it kind of looks like d squared y dx squared. That one isn't used as much. But if we continue on with the pattern, we see y triple prime or f triple prime of x. After that, you notice that the notation changes. We start using the actual number of the derivative. So the fourth derivative would be y in parentheses, what looks like an exponent of 4, and the same thing for f to the fourth of x, or the fourth derivative of x. And again, you notice that the other notations are done very similarly. So we can have a general notation for the nth derivative as y to the n, or the nth derivative of y, or f of n of x. Now let's start to use this notation to answer some questions. So first question says, find the first 4 derivatives of f of x. Now if we look at this, this is our simple polynomial function. So we can use our power rule and take the f prime of x, or the first derivative of x, is 18x squared minus 4x, and the derivative of any constant becomes 0. But then if we want to take another derivative, then we just follow the same process. So f double prime of x would be 36x minus 4. And again, we can continue on with this pattern to take the third derivative, or f triple prime of x equals 36. At that point, you notice we have a constant, which if you look, our original function was a cubic function. So once we take the third derivative of a cubic function, we get a constant function. And again, remember, we were asked to do the first 4 derivatives. So look what happens if we go to take that fourth derivative. F to the fourth of x, or the fourth derivative of x, well, the derivative of any constant becomes 0. And those will be our first 4 derivatives. Now, we can kind of have a rule here if we look and see this pattern. If we have some function of x, let's call it f of x equals some function to the nth power, if we take the f of n plus 1 of x, the n plus 1th derivative, then we should see that this entire function, no matter what it is, should end up being 0. And we can use that as a rule. Let's proceed on to the next question. So find the value of g double prime of 1, given that g of x equals x to the fourth minus x to the third minus 2x. Okay? So when we look at this, we have to start off taking our first derivative, or g prime of x equals 4x to the third minus 3x squared plus 2. Then we have to move on to the second derivative. So g double prime of x equals 12x squared minus 6x. At that point, we have to remember that that is our second derivative. So now if we need to do g double prime of 1, just like any function notation, we plug in 1 anywhere we see x. So it becomes 12 times 1 squared minus 6 times 1. Or 12 minus 6, which works out to be 6. So g double prime of 1 is 6. Now, in the last section, which isn't truly the last section, but in section 2.3, we saw that the velocity of an object moving in a straight path, neglecting air resistance, is given by the derivative of its position function. Now you remember that in the position function we sometimes label that as h, or h of t, referring to height. But not all position functions are dealing with height. They could be dealing with horizontal distance or diagonal distance. So what is generally notated for a position function is using the variable s. So s equals some function of time, or t. So remember, velocity is the derivative of time, or f prime of t. And we briefly talked about it, but the acceleration is the derivative of the velocity, or dv dt, which means it will be the second derivative of the position function, or f double prime of t. We're going to be using these ideas of the position, velocity, and acceleration function to understand different types of applications. Moving on to the next page. A ball is thrown upward from the top of an 80-foot cliff with an initial velocity of 64 feet per second. Give the position function, then define the velocity and acceleration functions. We've talked about the general formula before, that the position function is equal to negative 1/2 of g times t squared plus v sub naught t plus h sub naught. V sub naught is your initial velocity, h sub naught is your initial height, and g is the acceleration of an object on Earth due to gravity. Now, depending upon what we're dealing with, whether we're talking about feet or meters, that g will be one of two values. If we're talking about feet, then it is 16 feet per second. Oops, excuse me. It's 32 feet per second squared. If we're talking about acceleration due to gravity in meters per second squared, we would have 9.8 meters per second squared at any time. This constant is known as the acceleration due to gravity. So knowing these particular pieces, we can plug in to create our position function, which is s equals negative 1/2 times 32, since we're dealing with feet, t squared, plus the initial velocity is 64 feet per second times t, plus its initial height, which is 80, which simplifies to be negative 16 t squared plus 64t plus 80. And that is our position function. If we want to find velocity, remember from the last page, we want to take the derivative. So the velocity function, or v of t, is the derivative of the position function, which will be negative 32t plus 64 plus 0, but we'll leave off the 0. And finally, acceleration is going to be the first derivative of the velocity, which is the second derivative of the position. So the second derivative of the position would end up being negative 32. And you notice that we see that that is equivalent to our acceleration due to gravity. All the negative does is tells us that the direction that the acceleration is pulling down. Okay? Let's start to apply this when we start to see other types of acceleration and velocity functions. So in number 4, we see the velocity in feet per second of a certain automobile starting from rest is 80t divided by the quantity of t plus 5. Where t is the time in seconds, find the velocity and acceleration of the automobile at 10-second intervals from t equals 0 to t equals 60. In order to find the velocity, all we have to do is plug in. So v of 0 would be 80 times 0 over 0 plus 5, which is 80 over 5, which is 16. So if we fill into our table, when time is 0, velocity is 16. If we continue on, and if we go back and do v of 10, v of 20, v of 30, v of 40, we would do the same exact things that we did for v of 0 by plugging in. The values we should end up getting should be calculated below, or 53.3 feet per second, 64 feet per second, 68.57 feet per second, 71.11 feet per second, 72.72 feet per second, and 73.85 feet per second. So after 1 minute, the velocity of this car would be 73.85 feet per second. Now, one thing we have to find is the acceleration function in order to find the acceleration at these times. So in this case, we come back to our velocity function, which is v of t equals 80t divided by t plus 5, and we find our derivative. In order to do that, we have to do our quotient rule. So v prime of t will be the denominator times derivative of the numerator minus the numerator times derivative of the denominator all over the denominator squared. With a little bit of algebraic work, we should see that the 80t's cancel out, and we're left with 400 divided by the quantity of t plus 5 squared, which is our acceleration function. So again, if we want to find the acceleration at time 0, the moment we're starting, we plug in 0 for t, or 400 over 0 plus 5 quantity squared, which is 400 divided by 25, which turns out to be 16. So the acceleration of this car at time 0 would be 16 feet per second squared. Now, one thing you guys should notice is that a lot of times math teachers make mistakes. So if we go back to the velocity at time 0, we'll notice a big, big boo-boo here. And 80 times 0 is 0, which means that the velocity at time 0 is 0, which kind of makes sense if you think about it, because at time 0, the car is not moving. Right? So now if we come back to acceleration function, and we do a of 10, a of 20, so on and so forth, and plug in, we should get the following values. So the acceleration at 10 seconds would be 1.77 feet per second squared. The next acceleration at time 20 seconds should be 0.64 feet per second squared. 0.32 feet per second squared at 30 seconds. 0.19 feet per second squared at 40 seconds. 0.13 feet per second squared at 50 seconds. And finally, at 60 seconds, after 1 minute, this car is accelerating at 0.9 feet per second squared. You notice that that's a very small number. If you look at the acceleration, it looks like the acceleration drops off pretty quickly, but it slows down slower and slower and slower. It doesn't mean the car's moving slower, it just means there's less acceleration, which should mean, if you look at the velocity, that the velocity should start to be leveling out. And the difference between the velocities early on is a large number, but later on, you notice that there's not a lot of difference between the velocities. And that's due to the acceleration. So if we then were to graph these two, we should see this relationship. Looking closely, you see our velocity starts off low at 0, but then speeds up really quickly. But look at the velocity. It starts to level off. The acceleration was at time 0, at 16. But then what happens? It starts to level off because it's accelerating less and less. The acceleration is approaching 0. And you notice this relationship. As velocity starts to level off, the acceleration approaches 0. Now, if you go to answer this question, what can you include is happening about the vehicle speed? As we talked about, the vehicle speed is starting to level off as the acceleration approaches 0. Now let's look at one last problem. Use a graphing utility to graph f, f prime, and f double prime in the same viewing window. What is the relationship between the degree of f and its successive terms? Well, in order to do this, we need to know what f prime and f double prime is. So looking at this, f prime of x equals 2x minus 5, which means f double prime of x equals 2. You notice that degree of the first f of x is a degree 2. The degree of the first derivative would be a degree 1, and the degree of the second derivative would be a degree 0. So every time we take the derivative of a polynomial function, we decrease its power by 1. We end up getting these graphs, where f of x is our parabolic function, f prime of x is a linear function, and f double prime of x is our constant function. Hopefully these notes will help you out as you're progressing through the next 2 days of your homework. Have a good time.